Okay, anyways, chalo, let us start with the negative complex now. Okay, let us start with the negative complex. Can we? Okay, now same I hope that you have revised and come so that I can directly start with the negative complex. Yeah, I hope that. Okay, so negative complex. So let us start with the easy one. Suppose I have K4 FeCN6. Today I want to complete this, then I have to complete the isomerism, then I'll try to complete the VBT. Let's see. K4 FeCN6. Yeah, let us try this complex. Now, what are the different rules? See, same rule, same thing. Okay. First, now what do we call this? What do we call this which is outside our coordination sphere? Okay, Anthony. What do we call this? Yes. This is your coordination sphere and the elements outside the coordination sphere. Yes. And Sarjana, Anmoldeep, what do we call them? Prashanti, what do we call them? Correct, Sarjana. Correct. And Anmoldeep, central atom, which is outside the coordination sphere, not the central atom. And we do not say counter atom, we say counter ion. Counter ion. Okay, not a central atom. What central atom? Like, how can your central atom go into extreme left? The name itself says central. Yes, Anmoldeep, how you can say central atom? Okay, chalo. Anyways, it is the counter ion. Okay, so in the positive complex, the counter ion was on the end. That's why we used to write it in the end. We have to go as the complex is there. So first I'll write down the counter ion. Okay, then I'll write down the ligand. Okay, then I'll write down the metal. Okay, then I'll write down the oxidation state. Simple, simple. Okay, now the things that are going to change over here, especially your metals. Okay, especially your metal. We end our metal with 8s. We end our metal with 8s. Okay, we end our metals with 8. Okay, we end our metal with 8. So 8 is what we are looking at. So for example, I have over here Fe. Fe is iron. So we do not write ironate, we write ferrite. We write down metal as ferrite. What do we write it? We write it as ferrite. Okay. So similarly, I have some metals. So write down the names for that. So if you have cobalt, Prashanti, I will write it as cobaltate. Come on, write it down with me. Cobalt will become cobaltate. Okay, cobalt will become cobaltate. Okay, cobalt will become cobaltate. Okay, then your nickel will become nickelate. Nickel will become nickelate. Okay, then your chromium will become chromate. Chromium will become chromate. Okay, then your iron, just now I told you iron will become what? And iron will be ferrite. Iron will be ferrite. Okay, iron will be ferrite. Okay, then what we have? Copper. Copper. Okay, copper will be cuprate. Come on, write it. Copper will be cuprate. Okay, your silver will not be silverate. Okay, silver is called as argentine. So we will call it as argentate. We will call it as argentate. Come on, write it with me. Then we have lead. We have lead, which is Pb. Okay, so we call it as plumbate. We call it as plumbate. Okay, cobaltate, nickelate, chromate, ferrate, cuprate, argentate, and plumbate. Getting it? Okay, cobaltate, nickelate, chromate, ferrate, cuprate, argentate, plumbate. That's it. Okay. Write it down and done in the chat box. Write it down, done in that chat box. Come on, done in the chat box. And it's done, and Muldeep done, Prashanti done. Come on, done, Jason. Okay. So let us go ahead now. Let us come back to our compound. K4Fe. Without helping me, can you try? I have given you the rule. I have told you what you have to write first. Can you try? Yes? Come on, try. Chalo, try. I hope everyone is trying. Jason, Sajana, Sindhuja, you are late today. Sindhuja, I hope you are trying it. Okay. Okay. Very good. Okay. And Muldeep has given one answer. Anne has given one answer. Come on, Sarjana, Jason. Try. And Muldeep, there is a small correction in that. And Muldeep, we have a negative ligand. And there is a small correction in yours also. Counter ion correction. Do we write di, tri, tetra in the counter ion? No. Yeah, we do not write di, tri, tetra in the counter ion. That is understood from the oxidation state. Okay, Jason, what did I tell? Jason, first what you have to write? You have to write down the counter ion, then ligand, then metal, then oxidation state. Very good, Sarjana, but again the same mistake. Sarjana, look over here. Okay, look over here. I'll solve this one. I expected a lot. Okay, I'm sorry. Did not solve even one example and I gave you directly, but I was checking. But okay, good try. I appreciate it. Very good, Jason, Sarjana, and Muldeep. Very good. Good try. You were close. You all were close. Okay. So how to do this? First, we have to write, Jason, it is fine now. Okay. Jason, when I mean you have to write it in the beginning, that does not mean you have to write it in the end also. Potassium hexacyanoferrate 3 potassium. What is this? Yeah, Jason. Okay, look over here. I'm solving this, Jason. Wait now. I'm solving this. Okay. Tetra henta. Sorry. No di-tri tetra hexa penta. Nothing in the counter ion. I have told you this. Okay. Counter ion directly we write it. Let us say potassium. Okay. So I have a potassium over here. Then we go to our ligand. Okay. Ligand is cyanide. But Anmoldeep, negative ligand. What do we write? Yes, Prashanti. Negative ligand. We end it with O. I have given you a list. Yeah. So potassium hexacyano, and Jason, no space in between. No space in between. Hexacyano. Okay. Our ligand's over. Then after that we have the metal Fe. Now I have told you have to write down the ferrite. And what is the oxidation state over here if I calculate? Okay, some of you have given 2, Jason has given 3, and who else is given 3? Jason, how did we get 3 over here? So if I dissociate it, Prashanti, what charge will come on the complex? What charge will come on the bracket? Prashanti, what charge will come on the bracket over here? Prashanti, what charge will come on the bracket if I dissociate it? Yeah. Yes, Prashanti? Yes? Prashanti, you're not following? The charge, I have told you the cross method, isn't it, Prashanti? Over here 4, so that charge will come over here 4 minus. Okay, what we will come over here? 4 minus. 4 minus. Okay, so what we have, Jason, if the charge is 4 minus over there, Fe, I'll take it as X, cyanide is minus 1, so I have 6 cyanide, minus 6 is equal to minus 4. X is equal to 6 minus 4, X is equal to plus 2. Jason, how did we get 3 over there? So it is 2. Is it clear, everyone? Potassium hexacyanoferrite. Potassium hexacyanoferrite. Is it clear, everyone? Come on, give me yes or no. Is it clear? Okay, I'll give you one more now. I'll give you one more. Now I want the correct answer. I'll increase the difficulty level. Yes, Jason?
Anthony, sir.
Anthony. Yes, Anthony. What happened? What did you not understand?
The thing X minus 6 is...
Acha, look over here. Anthony, what we have, our complex. Anthony, keep your mic on for a minute. What complex we have over here? K4, Fe. Prashanti, you also look. K4, Fe, CN6. Okay, this is our complex. So if I dissociate it, Anthony, what will I get? If you remember, I have told you this method. If I have A4B, correct? So that 4 will come on the B. Okay. So if I dissociate it, this will get the 4 minus. I hope that is not a doubt, Anthony. Is that a doubt?
No, sir.
Okay. If it is yes, tell me. I'll explain you once again that A4B also.
Okay, sir.
Do not hesitate while asking doubts. Okay. So I have A. Okay. This is, let us say A. This is 4. This is B. The whole complex I am considering B because that does not dissociate. Okay. So when you dissociate compounds like A4B, how does it dissociate? That cross method, remember. Okay. Over here we have 1, A4B1. So on the top of A, I will get the 1. Okay. And first we have the positive ion. So I will get plus 1. Okay. On the top of B, I will get 4. Second, we have the negative ion. So I get minus 4. How many A I have? I have 4A. So 4A plus B minus 4. Is it clear, Anthony?
Yes, sir.
Okay. Yes, Arjun, I'll come to that. Then 4 minus over here, correct? So minus 4 is this because B is your FeCN6. Clear? No doubt?
Yes,
okay. Sir. Then we find out the oxidation state. Prashanti, how do we find out? I'll consider Fe because I am finding out the oxidation state of Fe. So Fe will be X. Okay. Now if you know what is the charge on Cn, the charge on single Cn, Anthony, it is minus 1. Okay. The charge on single Cn is minus 1 because it is a polyatomic ion and the charge on Cn is minus 1. For example, Anthony, HCN, if I dissociate, what do I get? Cn minus 1. So the charge on Cn is minus 1. How many Cn we have, Anthony? We have 6 Cn. So I'll get minus 6. Okay. And the whatever you have no on the top always come after equal to minus 4. Okay. So X minus 6 goes that side, plus 6 minus 4. This is plus 2. And that is how you got your 2. Clear, Anthony?
Okay,
oxidation state of Fe. Is it clear, Prashanti? Okay. Now coming to the point of Sajna. You can mute yourself now, Anthony.
Thank you, sir.
coming to the point of Sajna, why we are naming the potassium first? Because it is the rule, Sajna, that we have to go in the order from left to right. Okay. In the positive complexes, we had counter ion over here. Correct. That's why from left to right, we name the sphere first, then the counter ion. In the negative complexes, we have the counter ion first, then the negative sphere. So again, left to right, I have to name. So counter ion first, then the sphere. Yes, Arjuna? Is it clear? All the doubts clear? So that I can give you the difficult question now? Now you have taken my time for the
Sir,
doubts. Yes, and
show the last lecture.
okay, those who are writing, write it down. I'll write the question over here. I want answer for what should I give you. Okay, nice. K3, CO, CTO4 twice, Cl twice. You have taken my time in doubts. Now I am going to take your time in the questions. Let's see who gives the wrong answer. And those who do not know, I have given you list in the last lecture. So you have no reason. I do not know the name of this ligand. Yeah, what is that? I had given you this even in the bidentate, monodentate, tridentate list. Okay, you can check over there. Watch previous session, look at the previous PDF. I don't care. I'm not going to tell you the name until I get the answers. Can you repeat the question alone? I can. Or what? I said, Prashanti, over here, this is your question. You have to write down the name for this compound. That is the question. That's it. Okay. Yes, Sachna. I hope everyone is solving it. Sajna, you're solving it, no? Okay, we have some answers. We have some answers. Nice. From Anne, we have option answer. Okay. 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 Jason, we have the answer. Jason, you forgot about the oxidation state. And the metal also, Jason, look at it. Sindhuja, metal, look at it. Metal, metal, metal. And please, when you write down the answers, you know you have to just click on my name and then write it. Yeah. Do not write it in all chats. Click on that all chats. Over them, my name will be there. I hope everyone knows my name. Yeah, Prashanti? Know my name, no? Otherwise, someone will ask, who is your chemistry teacher? That long hair teacher, yeah? Sindhuja, correction in the metal and correction in the CL. Check. Sarjana, I'm waiting for your answer. Then I'm going to solve it. Anmoldeep has given answer? No? Anmoldeep, come on. If you want, you can unmute yourself and say if you want. If you are having difficulty to type such a long name. Sindhuja, wake up. Good morning. Yeah? Okay, Prashanti has written. Okay. Iron. When did I say iron? You do not have to write iron, Prashanti. Okay. Again, Anmoldeep, you have done mistake. Why you are doing all silly mistakes? You all are doing silly mistake. Okay. Mistake. I'll tell you what silly mistake you all are doing. Okay. Look over here. What silly mistake are we doing? Okay. What silly mistake are we doing? Our compound is what? K3. Okay. CO. Okay. C2O4 twice. Okay. C2O4 twice. Then Cl2. Then Cl2. Okay. So some of you are like, over here I have not written a what? I have written no clearly Cl2. Yeah. Anmoldeep, I have written no clearly Cl2. I have not written chloride only Cl, no, na? So again, potassium. You go step by step. No, although name is long, but not that difficult. Go step by step. Okay. I have potassium, and also the space should be between. So sorry, the space should be between counter ion and the complex. Okay, remember that. So potassium. Then what we look? We look at the ligands. Okay, we look at the ligands. Two ligands we have. We have a chlorido and we have the oxalate. Yeah, and we will write oxalate also as what? Oxalato. Oxalate is a negative ligand. Yeah, oxalate is a negative ligand, so it will be oxalato. So we have chlorido and we have the oxalato. Yeah, we have the chlorido, we have the oxalato. So over here, everyone, chlorido I have O, oxalato I have O. How many chlorido I have? I have two oxalato. Alphabetically, who comes first? That is also some of you have done silly mistake. Over here, you have to choose alphabetically. Chlorine comes first, C comes first, isn't it? So what I'll write? Potassium dichlorido. Yes, potassium dichlorido dioxalato. Yes, potassium dichlorido dioxalato. Okay. Then after dioxalato, what do I have? Yes, the ligands are over. Our dioxalato, it is over. Then we have to write down the metal. The metal is cobalt. I have to end with 8. Cobaltate all together. Cobaltate. Yes. And then the oxidation state. Then the oxidation state. What charge will come over here, Prashanti? Now I want answer from you. Yes, Anthony, what charge will come on the coordination sphere, the bracket? What charge will come? What charge will come over there? Very good, Prashanti. It is -3. Yes, oxalato, the single oxalato is -2. Yes, oxalato is -2. Do not forget. Why? Because you have COO minus, COO minus. This is oxalato. So single oxalato is -2. So Anthony, I will write X. I have 2 oxalato. So -2 into 2, that is -4. Cl is -1. 2Cl makes it -2 is equal to -3. -6 goes that side, +6, -3, that is +3. Are you getting it, everyone? Yes? So the answer is, this is your 3. This is your 3. Okay. Come on, tell me, is it clear, everyone? Yes, Anmoldeep. Yes, and Prashanti, Sarjana, Jason, Anthony, Sindhuja, Ragul. Is it clear? Come on, I want yes from everyone. Okay, so let's check who all have given correct. I'll start from the first one. Anne has written potassium dichlorido dioxalato cobaltate 3. So only thing you have to look at and is the counter ion, and there is a space between counter ion and the coordination sphere. Then I had Jason, potassium dichlorido dioxalato cobalt. Jason, cobaltate and oxidation state, you have to consider that, and do not give space between the ligands. Yeah, do not give space between ligands. Sindhuja, potassium dioxalato chlorido cobalt. Again, Sindhuja, you have to remember, we are going by alphabetic order. C comes first, then the O. Yes, C comes first, then the O. So dichlorido, dioxalato, and cobaltate. That also you have to look at. Okay, is it clear, Anmoldeep? Potassium chlorido, dioxalato, potassium dichlorido. Yes, Anmoldeep, that mistake you have done. Clear, everyone? Should I give you the last one? I hope I'll get the correct answer from that. Should I give you one more? Should I give you one more? Will you give me the correct answer? Yeah? Okay, sure. And add it one more in the list over here. Metal. Did I write platinum? Okay, platinum will become platinate. Okay, add it one more. Platinum will become platinate. Mercury will become mercurate. Okay, mercury will become mercurate. Okay, mercury will become mercurate. Okay, shallow. Platinate and mercurate. Okay, after that, what do we have? Okay, now one more, which should I give you? Just a minute, let me think. Okay. Chalo, try this. Suppose I have Na3. Okay, suppose I have Na3, CO, NO2, 6. NO2, 6. Come on, try this. Come on, try this now. And just give me a minute. I want correct answer from everyone this time, okay? Yes. Sodium hexanitrate 2. Oh, ho, ho, ho. Okay. Now one correction is there. I want to do this. Okay. See, NO2. When I say nitro, okay, what is the meaning of that? So there is a way to use nitro and nitrate too. Okay. Anmoldip has used one correct thing. Okay, nice. I liked it. See, NO2 is a ambidentate ligand, yes or no? NO2 is a ambidentate ligand. Okay. NO2 is an ambidentate ligand. Yes or no? Ambidentate means what? What is ambidentate? Sajna, Prashanti, Anmoldeep. And what is ambidentate? Jason. Ambidentate ligand. What is the meaning of ambidentate ligand? Bond through nitrogen. Like same ligand has a capability of bonding via nitrogen also, bonding via oxygen also. Two donor atom, but it uses only one. It uses only one. That is ambidentate. Over here, when I say NO2, okay, that means it is bonding via nitrogen. If I write ONO, then it means it is bonding via oxygen. Okay. Now, whenever I say nitro, I never say ONO. Okay, I never write ONO. If I have NO2, I have a complete freedom of writing nitro. Okay, because nitro meaning is NO2. Okay, nitro meaning is NO2. If I am writing NO2, that means nitro, complete freedom. But if some of you have used this word nitrito, okay, if I use this word nitrito, no, I have to mention nitrito is used for NO2 also, it is used for ONO also. So I have to mention that nitrito, it is bonding with what? Okay, nitrito, it is bonding with what? If it is bonding with oxygen, yes, I will write it as O. If I am bonding it with nitrogen, I will write it as N. Are you getting it, everyone? Yes, are you getting it? And it is a neutral ligand, by the way. It is a neutral ligand. Yes. So, two ways I can write this. Prashanti, do not change the tab. Two ways I can write it. Okay. Na is your sodium. So, sodium. What is my ligand? Hexa nitro. Okay. Hexa nitro cobaltate. Yes. What is the oxidation state you all have got? Let me check. Cobaltate. NO2 is a neutral. So 3, 3, 3, very good. So oxidation state will be 3. Okay. So one, this name, sodium hexanitrocobaltate. Second name would be sodium hexanitrito, sodium hexanitrito N. Sodium hexanitrito N, cobaltate 3. Are you getting it, everyone? Yes or no? Okay, cobaltate 3. Is it clear? Come on, give me yes or no. Is it clear? Sajna, is it clear? Jason, Anthony, Ragul, Sindhuja, Prashanti, everyone, is it clear? Okay, now one more rule that you should know is whenever we have something like, okay, write down this correct name, write down. Come on, write it down and done in the chat box. Come on, write it down and done in the chat box. Write it down and done in the chat box. So solve all the in your textbook. In your textbook, there are name. Okay. So please solve those. Please solve those. I'll give you more also. Okay, I'll give you more also. Look over here. You have to solve this. Okay, I'm putting it over here. Please solve it. Okay, please solve it. It's a request because your marks will be dependent on this. Okay, take a screenshot if you want. Take a screenshot if you want. Okay, then solve this also. Take a screenshot if you want, but please do it. Yes. Okay, then this also. Take a screenshot of this whole page. Take a screenshot of this whole page and kindly solve it and send it to me. Okay. Solve it and send it to me. Okay. I hope IUPAC is clear. Yes, everyone, I hope IUPAC nomenclature, positive, negative, everything is clear. Okay, now the one more rule, the last rule I want to tell you is when you have something like iron, okay, like for example, if I have something like CuCN6, okay, CuCN6, okay, CuCN6, let us say I have 3 plus, only this much, I do not have any counter ion, okay, I have only this much, Prashanti, and I have only this much. So what should I do? Okay, so write down the name according to our rule. We do not have counter ion, so in the end we'll add ion. Even if it is negative complex, follow the same rule, write down ion in the end. Are you getting it? For example, this will become hexacyano copper 3 ion. Are you getting it, everyone? Come on, mention it. Okay, so that in exam if it comes, you should not be confused. Because it is ion. Yeah, it is ion. And we are writing the oxidation state, so we know which ion it is. Okay, so no need of writing the charge. Write it and done in the chat box. Done. Okay. Now let us go to Werner theory. Okay, after this I'll give you the break. Don't worry, Prashanti. Okay, after this we'll take a break. Werner theory. Now Werner, who is this Werner? This is the first topic given in the textbook, by the way. Okay, before explaining anything, they have given this as a first topic, which is not correct. Okay, which is not correct, but they have given. Okay, so what is this Werner? Okay, Werner was the first person to study about the coordination compound. Okay, Werner was the first person to study about the coordination compound. Like I told you, if you remember, that we have double salt and the coordination compound. Yes, we have seen the difference between double salt and the coordination compound, correct? So similarly, Werner carried out one experiment. Okay, Werner carried out one experiment to understand the coordination compounds. Like what experiment he did? Look over here, I want complete focus. Look over here. So I have COCl3. Okay, this is what Werner took. Werner took one compound, COCl3, 6 ammonia. Okay, he took 1 mole. He took 1 mole of COCl3, 6 ammonia. Okay, and then he put excess. Okay, then he put excess of AgNO3. Then he put excess of AgNO3. Okay, so I have COCl3 and I have excess of AgNO3. Okay, so Prashanti, Sarjana and chloride has a brilliant affinity with silver. Okay, sorry, with silver. Your chloride has a brilliant affinity with your silver, that is your Ag. Okay, so what will happen? Ag we have in excess. Ag we have in excess. In 1 mole of this compound, I have 3 moles of chloride. Yes or no? In 1 mole of our complex, we have 3 moles of Cl. So if I put that and if I put AgNO3 in excess, what I'll get? I'll get the 3 mole of AgCl. I'll get the 3 mole of AgCl. Is it clear? Is this first clear, everyone? Is this clear? Prashanti and Sarjana, Jason, Anmoldeep, Sindhuja, is this clear? Okay. So what did Werner did? Werner took one complex or one compound, COCl3, 6 ammonia. Okay. Then he put excess of silver nitrate, that is AgNO3. Now we know that chloride has a brilliant affinity towards silver. So what did silver did? Removed all the chloride, that is 3 mole, whatever possible it is. It removed 3 mole and we have got 3 mole of AgCl PPT. Okay, precipitate. Nice. Now Werner was like, why to stop over here? So Werner removed, by heating, Werner removed that extra ammonia. Okay, and he took only 5 ammonia. Okay, he took only 5 NH3 and again he put excess of AgNO3. Again he took this as 1 mole. Now logically, like the answer is something else, but logically what should happen? Again, how many mole of AgCl I should get? Prashanti and Sarjana and Muldeep, Jason. Logically I am asking. Basically I am asking the wrong answer. Okay. Logically over here also, Jason, how many AgCl I should get? I have 3 Cl. So obviously doesn't matter what is there with the ammonia. I should get 3 mole of AgCl. Are you getting it, Sarjana, Jason? Yeah, I have 3Cl over there. I have excess of AgNO3. So obviously I should get 3 mole of AgCl. Yes or no? But your Werner sir, okay, Werner uncle was confused. Why? Because he got only 2 mole of AgCl. He got only 2 mole of AgCl. So Werner was like, Aing, what is happening? Why I am getting 2 mole of AgCl? Okay. So I have explanation for that. Okay. Then he removed one more ammonia, and Werner was like, okay, there might be some mistake with the 5 ammonia. Let us do it with 1 ammonia. Okay. So over here, again AgNO3, he took it in excess. Okay. He took it in excess. And over here, he got only 1 mole of AgCl. Okay. He got only 1 mole of AgCl PPT. So he was like, what is this? So from this, there are 2 types of valency. There are 2 types of valency. Do not write it down. I'll give you time to write it. There are 2 types of valency. One is your primary valency. Okay. One is your primary valency. And second is your secondary valency. One, your metal has 2 valency. Primary valency and the secondary valency. Now, secondary valency is fixed. Secondary valency is fixed by coordination number. It is fixed by coordination number. Okay, it is fixed by coordination number. Okay, it is variable. Okay, primary is variable. Now, fixed by coordination number means what? Look at this example. Cobalt. Okay, this 3. Let us come back. Let us come back on the screen. Everyone, look on the screen. Let us come back. Now, over here, cobalt. Okay, everything is done by cobalt. Cobalt has a fixed valency of 6. Cobalt has a fixed valency of 6. No matter what, 6 should be there. 6 atoms should be attached to the cobalt. Okay. So meaning what? Over here, cobalt, yes, 6 ammonia is attached. That's why, okay, chloride, you can go. Okay. Over here also, the secondary valence is fixed, that is 6, because the coordination number is 6. So it has only 5 ammonia. So it was like, no, the 1 chloride will stay with me like a hostage. Yeah, just like a hostage, 1 chloride will stay with me, 2 chloride can go. And that's why we got 2 mole of AgCl. Because the fixed valency of cobalt is 6. No matter what, it has to have 6 valency. Same over here. It has 4 ammonia, so it requires 2 more valency, and that is given by 2 chloride, and 1 chloride has gone away. That's why 1 mole of AgCl. Is it clear? Come on, give me yes or no. Is it clear, Sarjana, Anmoldeep, and Gopinath, Sindhuja, Ragul? Is it clear? Sarjana, is it clear?
Sir?
Sindhuja?
Sir?
Yes, Anthony.
Sir, can you explain the 2 mole of AgCl again, sir?
Okay, look over here. Look over here. So, I have this 2 complex. Okay, I'll write it over here. I have this 2 complex. Let us say COCl3. Okay, and 6 ammonia. COCl3 and 5 ammonia. Now, Anthony, cobalt has a fixed valency of 6. Cobalt has a fixed valency of 6 means what? Cobalt will make 6 bond anyhow. Cobalt will make 6 bond anyhow. It wants 6 bond. Okay, that is the main thing. Now, if you put excess of AgNO3, correct? So, I have 1 mole, 1 mole. In that, I have 3 chloride, 3 chloride. And I have excess of AgNO3. Okay. So, logically, all chlorides should come out. Anthony, logically, I should get 3 mole of AgCl. Yeah, because we have 3 chloride in the both cases. So, that should what happened. But only in the first case we got, because all the 6 bond, we had ammonia. All the 6 bond, we had ammonia, that is the secondary valency. Okay. Directly attached is your secondary valency, ammonia. Okay. Chloride was over just roaming around there. Okay. So Ag came, took out all the chloride with it. Okay. But over here, we have only 5 ammonia. Anthony, we have only 5 ammonia. We have only 5 ammonia. Okay. We have only 5 ammonia, 4 and 5th. So the 6th valency, okay, the fixed valency is taken by Cl. So out of 3 Cl, 1 Cl is fixed, attached, you cannot remove it. Only 2 Cls are roaming now. Only 2 Cl are roaming. That Ag has come and has taken away. That's why we have 2 mole of AgCl. Is it clear, Anthony? Is it clear?
Yes, sir.
Anthony? Huh?
Yes, sir. Clear, sir.
Okay. Okay, so this is your secondary valency. This fixed is called as secondary valency. This is called as primary valency. This is called as. So every complex has a fixed valency and a primary valency. Is it clear, everyone? Can I give you one question? Chalo, I'll give you one question and then we'll take a break. Okay, not a difficult question. It is straight from your textbook. You have to tell me the secondary and primary valency. Okay, you have to tell me secondary and primary valency. Look over here. You have to tell me secondary and primary valency. Okay, so over here, what do we have? Come on, read. So over here we have all the complex, and Jason, Sarjana, we have all the complex, and they have told you how many moles of AgCl you are getting. They have told you on the right hand side, you are getting 2 moles of AgCl. You are getting 2 mole of AgCl. So how many AgCl you are getting, they are telling you. So you have to tell for each complex, secondary valency and the primary valency. I hope not that difficult. Yeah. For each complex, you have to tell me secondary valency and the primary valency. Okay. Look at the first. Come on, tell me at least for the first. I have PdCl2 ammonia, 2 AgCl I have got. So what is my secondary valency? What is my primary valency? Okay. 0. No, not 0, not 0. Not 0, not 0. 0, 4, 4, 0, not 0, not 0, not 0. See, what I told you. You have PdCl2, okay, PdCl2 ammonia, okay. In the first case, okay, in the first case, correct, Anmoldeep, correct, Jason, in the first case, 2 Cl are going. So that is your primary valency. Are you getting it? And that is your primary valency. That is not fixed, that is not attached. But this 4 ammonia are remaining. Okay, so that is attached. So the secondary valency is 4, primary valency is 2. Are you getting it? So basically these are your primary valencies only. Yeah? How many mole of AgCl you will get? That is your primary valency. Okay, remaining what is fixed over there is your secondary valency. Are you getting it, everyone? Okay, 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 nice. I hope everyone is clear with it. Yeah, and do not write the random number 6, 2. How will I come to know that this is the answer for first, this is the answer for second? And Muldeep, Sindhuja. Yes, Arjuna, I hope it is clear. Is it clear, everyone? Come on. Okay. Chalo, let's take a break now. I am happy that you have got it. Okay. After the break, we'll start with the isomerism. Okay. 8:05. Let's begin at 8:15. Okay. Please do not come late. Come by 8:14. I have to start by 8:15. Okay. Please do not come late. Yes, everyone, come on, back in the chat box. Come on, back. Prashanti, Anthony, are we back? Ragul, Gopinath, Anmoldeep. Chalo, let us continue. Okay, let us continue. Now, from this, okay, from this, where were we? Now, let us start with isomerism. Let us start with isomerism. Come on, tell me, what is isomerism? Everyone, you must have done this in organic also, if I'm not wrong. Now, this is the inorganic chemistry is isomerism. What is isomerism? Yes. What is isomerism? Yeah. Isomerism. What do we mean by isomerism? Yes, isomerism. Okay, very good. And yes, Sindhuja, Jason, Sarjana, what do we mean by isomerism? Anthony, Prashanti, what do we mean by isomerism? Yes, I'll give you one organic chemistry example. Okay, I'll give you one organic chemistry example. Okay, so for organic chemistry, okay, for organic chemistry example, let us consider this. What is this? CH3CH2OH. Okay, which compound is this? Yes, CH3CH2OH. What is this? This is nothing but your, yeah, Sarjana. What is this? CH3CH2OH. Correct. And Sarjana, what is this? Correct. Ethanol. So in the ethanol, I have 2 carbon, 6 hydrogen. O. Over here also, I have 2 carbon, 6 hydrogen. O. Yes. So I have ethanol and ether. Same thing, but 2 different functional groups. This is ether, that is alcohol. Are you getting it? I have the same molecular formula, that is C2H6O, but different structure formula. That is your simple isomerism. That is your simple basic isomerism. Is it clear? Okay, that is the isomerism. Same compound. No, chemical formula is same, Sarjana. Chemical formula is same, but the structural formula is different. The structure is different. Okay, the attachments are different. For example, look over here. So in your inorganic chemistry, in your coordination compound, okay, we have different type of isomerism. So first we have the structural, and second is your stereo. So let us start with structural. Okay, structure, that means something related to structure would be there. Correct. So first is a structural isomerism. Okay, structural isomerism. So in the structural isomerism, we have the first one, that is your ionization isomerism. That is your ionization isomerism. That is your ionization isomerism. Okay, ionization isomerism. Okay, ionization isomerism. So over here, ionization isomerism I have. Okay, so ionization, as the word says, something related to ionization. Yeah, so just like over here, everyone, we had 2 structures to compare the isomerism. Same thing, we have to see the 2 compound to compare the isomerism. Now what is this ionization isomerism? Look over here. So the counter ion and the ligands get exchanged. For example, look over here. Suppose I have a complex like CO NH3 5 Br is my ligand. Okay, SO4 is my counter ion. So over here in your ionization isomerism, 2 compounds, the ligand and the counter ion gets exchanged. So ligand and the counter ion gets exchanged. So what I have? CO NH3 5 SO4 Br. CO NH3 5 SO4 Br. So whenever the counter ion and ligand is exchanged, we call it as ionization isomerism. Are you getting it, everyone? Are you getting it? How many of you know Akshay Kumar? Anyone? Bollywood hero? Anyone? He has worked even with Rajnikant in that Robo movie, yeah? No one? Anyone know him? Yes or no? Jason, Sarjana, and we know Akshay Kumar? Jason knows it. Sarjana, do you know? And do you know? No. Achha, okay, anyways. Because he had one meme. Okay, I remember one meme, okay, where he makes a gesture like this, that we use, regularly whenever something is exchanged. So we used to use that meme. This one. Okay. So here SO4 and Br is exchanged. SO4 and Br is exchanged. Okay. This was a meme. Okay. Shall like see, like the meaning behind that meme is like that. Okay, like we have meme like this. Or bapre, not such a large meme. Okay, look over here. So the meme actually goes like this. Meme actually goes like this. Okay, meme actually goes like this. Yeah, like the exchange meme, eating once out, working out daily. No, eating out daily, working out once a week. So similarly, we have the meme for the chemistry also, where your ligand and counter ion are exchanged. Just a minute, everyone, till them. You write it down. You write it down. Just a minute. Is it clear, everyone? Okay, not the meme, but the concept. Huh? Otherwise, you'll draw the Akshay Kumar in the exam. Yeah, in the ionization isomerism. Okay, what has happened? The ligand and the counter ion is exchanged. The ligand and the counter ion Sarjana is exchanged. Okay. Then the next what we have after ionization, we have something called as hydrate isomerism. We have something called as, give the heading, hydrate isomerism. Hydrate, what do we understand from this word hydrate? Yes, Sarjana? Sarjana, sorry. And what do we mean by hydrate? Jason, hydrate, where do we use this word hydrate? What is it related to? Yeah? Correct, Sarjana? Sarjana, it is Sarjana. What is it? Or Sarjana? Sarjana.
Sir, it's simply Sarjana, sir.
Do your friends also call you Sarjana?
Sir, I can't hear you properly, sir.
Do your friends also call you Sarjana?
No, sir, they call me Sarju or Sarjan.
Sarjan. See, that is nice. Sarjan, I do not have to say ah after
Sir,
that.
actually,
Okay.
they call me Sarjan Singh. I don't know why, sir.
Okay. Chalo, anyways. But you can become actual surgeon, isn't it? If you clear the NEET, you can actually become surgeon. Yeah? Fine. Okay, hydrate. Yes, hydrate, correct, surgeon, correct. And we have the water, correct? Water. So something related to water. Okay, so it is same like your ionization isomerism. Only thing is your water is getting exchanged. Either your counter ion would be water coming inside, or your ligand would be water going outside. Okay, so for example, if I have a complex like, let us say CrH2O6 Cl3. Okay, so my hydrate isomer will be what? One of the water ligand will get exchanged with the counter ion. Okay, Cl2 H2O. Okay, one more I can draw. One more H2O getting exchanged with the Cl. Are you getting it, everyone? Come on, draw it. You draw it yourself now. Jason, are you getting it? Same. What has happened? Same ionization, same exchange. Only thing is over here, my ligand is water. Okay, so if water molecule is getting exchanged from the ligand to counter ion or from the counter ion to ligand, it is hydrate isomers. Come on, write down the example, draw the third molecule, and done in the chat box. That is your hydrate isomerism. Come on, write it down and done in the chat box. Done. Sarjan, Prashanti, Jason. Come on, done. Okay, shalom. Let us go ahead. So after hydrate isomerism, the next we have is the coordination isomerism. Okay, next we have coordination isomerism. Coordination isomerism. Something is going to happen with the coordination. Yeah, something going to happen with the ligands. Okay. So what happens, you know, in the coordination isomerism, write it down. All of the ligands are exchanged. All of the ligands are exchanged. All of the ligands are exchanged. Okay. For example, I have a complex like, let us say, see, we have seen a positive sphere, we have seen a negative sphere. I can also have a complex with both sphere joining. I can also have a complex, both sphere joining each other. This would be positive, this would be negative. Okay, like a neutral. Okay. So, when all of the ligands are getting exchanged, for example, suppose I have PT NH3 4, PT NH3 4, and I have Cu. Okay, I have CuCl4. Okay, PT NH3 4 and CuCl4. All of the ligand will get exchanged. Your Cu will have ammonia. Okay, Cu have the ammonia, and your PT will get the Cl. Are you getting it? So such isomerism where all of the ligands are exchanged, we call it as a coordination isomerism. I hope it is clear. Yes or no? Jason, is it clear? Come on, write down and done in the chat box. Write down the example and done in the chat box after that. Done. Then after coordination isomerism, okay, we have something called as linkage isomerism. Okay, we have something called as linkage isomerism. Okay, we have something called as linkage isomerism. Something related to linkage. Now this is there. Write down in the bracket with the ambidentate ligands. With the ambidentate ligands. I hope now everyone is clear with the ambidentate ligand. Yeah. Ambidentate ligand. So what will happen over here? Everything will be same, but ambidentate ligand attachment would be different. Ambidentate ligand attachment would be different. For example, look over here, everyone. I have cobalt NH3 NO2 Cl. Okay, NH3 NO2 Cl. So my ambidentate ligand NO2 will have different attachment in the linkage isomer. So I will have cobalt NH3 NO Cl. Are you getting it, everyone? Yeah, you can see over here, Prashanti, the linkage has changed. Nitrogen is attached, over here oxygen is attached of the same complex. Is it clear? Come on, write down the example and done in the chat box. Come on, write down the example and done in the chat box. Okay, then we have the polymerization isomerism. We have the polymerization isomerism. Polymerization isomerism, same thing. Okay, something is going to happen with a polymer. Okay, so what is happening over here? Your monomer will become dimer, trimer, etc. For example, I have Jason over here, PT NH3 twice Cl2. Okay, PT NH3 twice Cl2. Okay, suppose this is my complex. Okay, so the polymerization isomer of this complex would be what? How many platinum we have, Prashanti? We have 1 platinum, we have 2 ammonia, we have 2 chloride. Okay, now doesn't matter who is with whom. In the polymerization isomer, it is going to become polymer. So polymer means what? Your monomer is going to become a dimer. Your monomer is going to become a dimer. So over here, I have a platinum. Over here, I have a platinum. So platinum will become dimer as 2. Your ammonia, which is 2, will become 4. Your chloride, which is 2, will become 4. So what will I get over here? I will have 2 platinum. Now 2 platinum, I cannot write it in a single coordination sphere. Are you getting it? And Prashanti, Sarjana, I cannot write platinum 2 metals in a single coordination sphere. So I will have a complex which have two coordinations here. Okay, one where I have platinum and ammonia 4, and I have one with the platinum with 4 here. I hope Jason, you're getting it. Prashanti, Sarjana.
Sir,
Yes, who's this? Jason?
sir, should you write chlorine in another
Huh?
another complex, sir? Should you write chlorine in another complex, you can write, sir.
I did not get your question. Come again?
Sir, should you write the chlorine in another complex, sir? T4.
Yeah, you have to write it in other complex. No, that is what I'm saying. In the polymer, your one platinum has become twice. Okay. Your ammonia has become 4. Your Cl has become 4. Okay. But the coordination of platinum you cannot change. No. The coordination number of platinum has to be 4. So in single platinum, I cannot write ammonia as well as chlorine. Okay. That's why I have written NH3 4Al4 in other complex. Okay, but they are together. Okay, other complex means what? This is plus, this is minus. Okay, they are together. Are you getting it, everyone? Yes or no? If it is not, please tell me. I'll explain once again. And Prashanti, Sarjan, is it clear? Okay. Shalom. Let us go ahead. Then the next we have is the coordination isomerism. Okay, the last one, coordination isomerism. Coordination isomerism. Okay, now there are coordination position isomerism. Sorry, coordination, write down coordination position isomerism. Okay, coordination position isomerism. Now, now over here, coordination position isomerism. Okay, so what is happening over here is you have the polynuclear complexes. You have the polynuclear complexes. Okay, so poly is what? Polynuclear complexes means what? Okay, so over here I will have a bridge like ligands. I will have a bridge like ligands means what? Look over here, everyone. I will have a metal, cobalt, okay, where I have a bridge like ligand with ammonia over here, one more ligand with oxygen, okay, and I will have more ligands. Let us say I have 4 ammonia over here, okay, I have 2 ammonia and 2 Cl over here. Okay, this is not there maybe in your textbook. Okay, this is from the reference book, but you should know this. You should know this. Okay, not NH3 over here, it should be NH2. 2 bonds it is making, no, it should be NH2. Okay, so this is your polynuclear complex. This is your polynuclear complex. Polynuclear complex. Okay, polynuclear complex. Now, in the coordination isomerism, okay, in your polynuclear complex, the ligand will change the nuclear position. What is the meaning of that? That one of the ligand will jump from over here and that ligand will come over here. Okay, one of the ligand will go over there, the other ligand will come over here. Okay, because cobalt coordination number is 6, that is not going to change. Okay, so let us say ammonia from this is exchanged with the chloride over there. So what I'll get over here, Surgeon, I will have 3 ammonia, okay, and 1 chloride. Okay, 3 ammonia and 1 chloride, which is attached to cobalt. Then I have a bridge ligand of ammonia, cobalt. I have chloride over here. Then the Cl is exchanged, ammonia is added. So I have 3 ammonia over here and 1 Cl. Are you getting it, everyone? Come on, write it down. This is your coordination position isomerism. Coordination position isomerism. Strictly for your competitive exam, may not be there in the textbook. May not be there in your textbook. Come on, write it down and done in the chat box. Should it be Cl at the bottom? Where? Sarjana? Oh, Sarjan is active today. Nice. It is O2. Nice, Sarjan. As I call it Sarjan, Sarjan has become active. Nice. Okay, it has to be O2. Okay, it has to be O2. Correct? The bridge ligand will not change, no? Yeah? It has to be O2. It is like your ligand has got a bridge. Yeah, it's to go over to that side, isn't it? Done. Everyone, come on, write it down. Done. Done. Okay. Now I have a choice between teaching you stereoisomerism right now or the valence bond theory. Come on, you choose. Stereoisomerism or VBT. Stereo or VBT. Come on. If you want stereo, write down 1. If you want VBT, write down 2. Obviously, the remaining part I'll take it in the next lecture. But what should I teach now? Stereo 1, VBT 2. Write down in the chat box. Highest vote, I will start. 1 or 2. Stereoisomerism or valence bond theory. There is no option 3, none. Okay, I cannot leave you early. Otherwise, you will select 3, none. Yeah. Okay. 1, 2. Do not make a tie in this. If there is a tie, I will not teach anything, isn't it? Or a better conclusion, I will teach both. I'll extend the lecture. Yeah. If there is a tie. Yes, what should I start and Shanti? 1 or 2? I have equal votes till now. Some of you have said 1, some of you have said 2. I have the equal votes. Okay, anyways, I'll start with stereo. Chalo, no worries. No worries. If we do not complete VBT, we'll take the class assessment, 2 class assessment in the same class, next class. Okay. I'll start with the stereo. Let's go in the order. Okay. Stereoisomerism. Let us start with the stereoisomerism. Okay. Stereoisomerism. Stereoisomerism. Now, stereoisomerism means what? Over here, even your chemical formula is also same. Okay. Only thing is the complex arrangement of the atom will change. Complex arrangement of the atoms will be will change. For example, look over here, Sarjan, Jason, look over here. So first, in the stereoisomerism, what we have is a geometrical isomerism. Okay, it is there in the organic chemistry also. Geometrical isomerism. Geometrical isomerism. That means our cis and trans. Geometrical isomerism. Okay, geometrical isomerism. So for example, first let us consider we have a square planar complexes. We have the square planar complexes. Square planar complexes. Okay, that means what? What will be the coordination number for the metal in the square planar complexes? Jason, Sarjan, and yes, Prashanti, Gopinath. What will be the coordination number of metal with the square planar complex? Did you get my question, everyone? Correct, Jason. And what will be the coordination number? Yes, and Sanjana, what will be the coordination number? Okay, so in the square planar complexes, what is the coordination number? Coordination number means how many bond does it form? Surgeon. Okay, so coordination number is 4. Coordination number is 4. So let us say I have a complex like Ma2B2. I have a complex like Ma2B2. I have a complex like Ma2B2. Okay, so over here Ma2B2. Okay, over here cis and trans. Obviously, we know what is cis and trans, and what do we mean by A and B? That means we have two different ligands. We have two different ligands. So, what is this? Is this cis or trans? MAA, MBB. Yes, what is this? You should be knowing this without teaching. Is this cis or trans? Yes, Arjun, Jason, and is this cis or trans? If identical elements are in the opposite, we call it as trans. We call it as trans. Okay, identical BB in the opposite, we call it as trans. For example, if I have a complex like, let us say platinum, okay, ClCl, ammonia, ammonia, ClCl, ammonia, ammonia. Okay, this is a trans, for example. Are you getting it, everyone? Yeah, and then change it anything, it will become cis. Okay, for example, MAABB on the same side. On the same side, it becomes cis. Okay, draw the cis for the example with the same ligands. Is it clear, cis and trans? Not that difficult, I know. Is it clear? Cis and trans. Okay, cis and trans. So when you have Ma2B2 type of complex, you can have two geometrical isomers. You can have two geometrical isomers. Is it clear? Come on, write it down and done in the chat box. Draw the cis. Okay, with the same ligands and the metal, draw the cis. Draw the cis with the same metals and the ligand. Same metals and the ligand, draw the cis and write down the done in the chat box. Come on, Surgeon and draw.
Sir,
Yes, Jason.
sir, whether ethylene diamine is a square planar complex?
Ethylene diamine, we can have it in a square planar complex, but your ethylene diamine is your bidentate ligand. Okay, ethylene diamine have a bidentate ligand. So for that, let us consider two bidentate ligands. Okay, let us consider two bidentate ligands. So in that there will be no cis and trans. Yeah, there won't be any cis and trans. Only thing in the ligands like this, look over here. In the ligands like where you have, for example, platinum, GLY twice. Do you remember what is GLY? What is GLY? Look into the list. Surgeon and Jason, look into the list. What was GL? What was GL? Only in this we will have cis and trans. What is GL? Look into our list.
Glycinate.
Glycinate. Do we know the structure of glycinate? Look over here. Yes, we know the structure of glycinate. Okay, glycinate is like this. Suppose I have platinum. Okay, my glycinate, I have NH2. Okay, and oxygen. Okay, NH2 and I have oxygen. Like glycinate is like this. CH2. Okay, then I have CO. Okay, I have the oxygen and the bond over here. Okay, this is your glycinate. NH2, CH2, COO. And if I have NH2, NH2 on the same side, if I have NH2, NH2 on the same side, okay, this is my cis. This is my cis. Okay, and the trans would be what? Trans would be PT, NH2, NH2 opposite. NH2, NH2 opposite, OO opposite. Okay, are you getting it, Jason? Yeah. So only in this type of square planar complexes where we have bidentate ligand, unsymmetrical bidentate ligand. Okay. Ethylene diamine, both of them are NH2. Okay. So no cis and trans in that. Getting it, Jason? Yeah, in the ethylene diamine, I have CH2, CH2, correct? So both of donor are your NH2. Okay, so no cis and trans in that. CH2, CO, come on, write down this. This is your cis, this is your trans. Come on, draw it. Draw it. Draw it and done in the chat box. Draw it and done in the chat box. Draw it and done in the chat box, everyone. Surgeon, Jason, come on, done in the chat box. Okay, chalo. Let's go ahead after cis and trans. Your Ma2B2, we have a complexes also like Ma2BC, Ma2BC. In that also we have cis and trans. In this also we have cis and trans. Okay, your cis and trans, Jason, Surgeon, and will be depend on A. If your A is opposite, it is trans. If your A is side by side, it is cis. If A is opposite, it is trans. If your A is side by side, it is cis. Come on, draw this. I'm not giving you example now. It is understood, I hope. Yeah. That means I have three types of ligand. That means I have three types of ligand. Like for example, platinum, take any ligand, Cl, twice, NH3, NO2. Okay. Ma2BC type of ligand. Ma2BC type of ligands. Or complex. So trans and cis. Come on, draw it and done. Draw it and done. Come on, draw it and done. Done. Okay. Then we have all of the four different M, A, B, C, D. Okay. In this we have three types of isomers. Okay. We do not say cis and trans in this. We do not say cis and trans in this. What we do, Jason, we just hold one at a time. Like for example, suppose I have A, B, C, D. What I'll do, Surgeon, and I'll keep the A at one place. Okay, and I'll move all three. Okay, so this is the first one. Okay, let us say I have moved D over here to B. So M, A, D. Then what we have? B over here. Everything will move ahead. And then C over here. Similarly, again movement. Again, it will move. A is constant. So M, A as it is. Now C will be over here. B will be go ahead. This will become D. This will become B. I hope you are getting it. Yes, Jason, Surgeon, and then if I do one more rotation, everything will come back to its original position. Yes, everything will come back to its original position. So that is why when you have four different type of ligands, this is how it is attached. This is how it is attached. Done. Come on, write it down. Jason, Surgeon, Prashanti, Ragul, Gopinath. Done. Okay. Next. Okay. Now next we have is the octet. octahedral and the tetrahedral complex. Okay, we have the octahedral and the tetrahedral complex. Okay, octahedral and the tetrahedral. So we do it for octahedral. Okay, we do it for octahedral. Octahedral complexes. Octahedral. What is the coordination number in octahedral? Everyone? Metal coordination number in octahedral. How many bonds a metal make in octahedral? Sarjan, Jason, and Gopinath, Prashanti. Octahedral complex, a metal will make how many bonds? Jason? Yes, how many bonds? What will be the coordination number in the octahedral? Why do we call it octa then? What is octa in octahedral? Jason says 8. What is octa in octahedral? Yes, Sarjan. Why do we call it octa? Octa means 8. We know that. So Jason, the coordination number is 6, not 8. Okay, it forms 6 bond. How? Look over here. We have a metal. We have a ligand. Let us say A. Okay. So this becomes a square planar. Okay. And we have, let us say, A at the top, A at the bottom. Okay, this is octahedral. So metal coordination number, Jason, it is 6, not the 8. It forms 6 bond. Now why we call it octahedral? Okay, that is because it contains 8 sides. 8 sides, Surgeon. So if I join this, okay, this is the first side from the top. Then if I join this, second side on the right. If I join this, third side on the back, and the fourth side on the left hand side. So 1, 2, 3, and 4. 4 sides on the top, 4 sides. Similarly, if I attach over here, I'll get the same thing. 4 sides in the bottom. That's why we call it as octahedral. Are you getting it, Jason? That is why the name octa, not the coordination number. Coordination number remains 6. Okay? Coordination number remains 6. Okay, now over here, you have 3 types of complexes. Okay, I'll tell you all 3. That is Ma4B2 type of complex, Ma4B2 type of complex. So in that, obviously, how I will do cis and trans depending upon B. If B and B are opposite, I am going to get trans. If B and B are opposite, I am going to get trans. If B and A are opposite, then no matter what, I will have cis. I will have cis. Yes. So AA, BA. AA, BA. Okay. This is just cis and trans. Okay. Now the interesting part in octahedral is with Ma3B3. Okay. Is it with Ma3B3? Okay. This is clear. Okay. Interesting part is with Ma3B3. Okay. This gives 2 new isomers called as facial and meridonial. Facial and meridonial. Facial and meridonial. Facial and meridonial. Okay. Facial and meridonial. So over here, what is facial? What is meridonial? Look over here. It is in the name. Face. They are in the single phase. Now look over here. So octahedral I have. Okay. A. Okay. And in the exam, if this comes to draw, no, please draw this as dotted lines. Okay. Draw this dotted lines. Otherwise, they can cut your marks. Yes. Why I'm drawing a dotted line? What is the difference between both of them? Dotted line and a solid line. What will happen if I can make a solid line also? How does it make a difference? Surgeon, Jason, and yeah, how does it make a difference if I draw a solid line or a dotted line? Yes. But if you draw a solid line, they will give you 0. They have a 100% authority to give you 0 in the book. board's exam, if you draw it, what is the difference? Okay. Jason. Sarjan, what is the difference? Come on, tell me. Solid line and the dotted lines. So the difference is one will take more ink, one will take less ink. Yeah. See, see dotted line we draw, Sarjan, Jason, dotted line we draw to understand the geometry. Okay. The solid line, they are the bonds. They are the bonds. If I draw a solid line between A, B, A, that means B and A are bonded to each other. B and A are bonded to each other. If I draw a solid line over here, that means B and A are bonded to each other. Are they bonded? They are not bonded. We are just showing, we are just making a structure. Just like we make the names in the stars, isn't it? Yeah? Isn't it? Surgeon, you do it. Yeah? Those are constellation. Okay. Okay, anyways, I'll explain you constellation some other day. Here, facial and meridional. Look over here. Now, what is facial? What is meridional? Okay. Facial means you have one ligand at one face. Now, what is that? Look over here. I will have A ligand over here. Okay. B, 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 B. So if I join this, everyone look at this carefully, okay? I want you to imagine. Look at this carefully. So let me draw. So this A, they are at a single face. They are at a single face. So if I join this, they are at a single face. Are you getting it? They are at a single face. Same is with the B. If I join it with metal, okay, if I join it with metal, they are at a single face, two faces. Yeah, two faces. That's why we call it as what? Facial. That's why we call it as facial. Are you getting it, Sarjan, Jason, and Prashanti? Are you getting it? Yes, that is your facial at one face. Now, meridional means what? Apart from facial, meridional. Now, how to avoid in the exam getting confused between facial and meridional? Okay, your meridional is a trans. Meridional is a trans. That means what? Instead of AB, in the meridional, simply write AA. Done. Simply write AA. You will not do any mistake. Then make another A anywhere. Then make another A anywhere you want. Make another A anywhere you want. Okay. So let us say I have made a A over here. Okay. B, B, B. So they are not at a single face now. They are not at a single face. Are you getting it, everyone? This is your meridional. This is your meridional. Come on, write it down. Everyone, write it down and done in the chat box.
Sir, can you say meridional face again, sir?
Who's this? Jason? Was it you? Acha. Look over here. Jason and meridional. Not Jason and meridional. Facial and meridional. Okay. Facial and meridional. Look over here. So facial, it's in the name. It's in a single face. Okay. It is in the single face. Like the opposing face. Okay. Two opposing face. Look it like that. Two opposing face. Okay. So whenever I have Ma3B3 type of complex, only this will show facial and meridional. Okay. Only this will show facial and meridional. Ma3B3 type of complex, because there is a chance of them to become face in single face. So A, they come in a single face. If you look it like this, okay, aren't they making a face? Yeah, they are making a face. So when these three are on the one side, remember like this, these three are on the one side, okay, and the other three on the other side, other three on the other side, B, B, B. Okay, this is your facial, two opposite face. Are you getting it, Jason? This is your facial. Is it clear? Then look at the meridional. Your meridional, make over here in the facial, A and B are opposite, correct? Simply in meridional, make AA on the opposite. Done. Then it cannot be facial because AA are in the opposite face. It can never be a facial then, correct? So let us say A over here, B over here, B over here, B over here. Okay? Those three are not together now. So it is meridional. Clear, Jason? Is it clear, surgeon? And is it clear? Facial and meridional. Facial and meridional. Facial and meridional. Okay. Then we have VBT. I think I should not start VBT. Okay, but let me give you a few hints for optical isomerism. Okay. Well, let's do one thing today. Okay. It is 9:04. We'll continue till 9:20. Okay, we'll continue till 9:20. Let's not do the, what we say, class assessment today. In the next lecture, because I have put VBT questions also in the class assessment. Let me check. VBT questions would be there. Or no, not there. Isomerism, then we have optical. Okay. No, VBT is there. VBT is there. Okay. So VBT questions are also there. So VBT we have not done. So let's do the class assessment, both of them in the same class in the next lecture. Okay. Let's do the optical isomerism. Okay. Don't worry. I know you are tired. Will not extend much. I'll try to leave you early. Okay. Optical isomerism. Optical isomerism. Okay, in the organic chemistry, many students do not understand only this. Okay, what is optical activity? Yes, when do we say compound is optically active? Anyone, come on, tell me. Jason, surgeon, and when do we say compound is optically active? Yeah, optically active. Prashanti, are you fine? Prashanti? Yes, correct, sergeant. What else? What else? It is only chiral carbon is not the necessity. Yes. When optical active means what? It rotates the plane of polarization. Okay. It rotates. We'll go into details when we do the organic. For now, remember, it rotates the plane of polarized light or plane polarized light. Okay, it rotates the plane polarized light. That time we say the compound is optical active and it shows optical activity. Okay, it shows optical activity. Okay, so optical activity, there are some requirement. Okay, the main requirement for the coordination compound, we are not doing organic, so forget about chiral carbon. There is no chiral carbon. In the organic also it is the requirement. One is the chiral carbon for organic. Another, the most important is it should not contain, write it down in the bold, it should not contain plane of symmetry. It should not contain, like if I cut that molecule, it should not divide into two identical half. Identical, okay? It should not contain plane of symmetry. Okay, so if I cut that molecule, it should not be identical. That is the point. Are you getting it, Sarjana? Okay, for example, suppose, Jason, look over here. Suppose I have A, B type of complex. Okay. Now, if I cut it from between, yeah, if I cut it from between, Sarjana, if I cut it from between and, okay, if I cut it from over here, what will happen? Your metal, or the metal and A, they will cut into equal half. Yes. And your B and B also same. So everything is getting equally cut off. Are you getting it, Jason, Sarjana? So this will become optically inactive. It will become optically inactive. Are you getting it? And Sarjan, Jason, come on, tell me. It will be optically inactive. Why? Because there is a plane of symmetry. There is a plane of symmetry. Suppose I have a complex like, look over here, Jason, and suppose I have a complex like this. Will this be optically active or inactive? Will this be optically active or inactive? Yeah? Will this be optically active or inactive? Yes, optically active. Because if I cut from the bottom, yeah, it is unsymmetrical. B and A are not identical. Even if I cut it from the top, at the left hand side I have A, on the right hand side I have B. Okay. So, and what is this? Is this facial or meridional? Doesn't it look similar? Okay. So this is optically active. I hope optical active inactivity is clear. Yeah. Optically active. Yeah. So you have, let me give you a few example. Okay. Let me give you a few example. Okay. Suppose now this is explored mostly in your, what we say. This is mostly explored in your bidentate and tridentate ligands. Okay. Bidentate and tridentate ligands. Okay. Now even your compounds like when all of the ligands are different, M, A, B, C, D, E, F. Okay, suppose A, B, C, D, E, F. Okay, even this will be optically active. This will be optically active. Yeah, optically active. Are you getting it? Optically active. Okay, then we have the bidentate ligands. We have the bidentate ligand. Okay, for example, cobalt, En thrice. I'll tell you how it looks like. Look over here. Your cobalt En thrice look like this. You have a cobalt, okay. En, is it a bidentate, tridentate, monodentate? Yes. Is it bi, di, tri, mono? What is it? Which dentate is this? Correct. It is a bidentate. Okay, it is a bidentate. So look over here. It is like this. It is like this. Look over here. So I have a bonds. Okay, you have to octahedral bonds. You have to make it like this. Okay. So En. Okay, I have a En like this. Okay, one En like this. My another En can be like this. Another En can be like this. Okay, and my this En can be like this. Are you getting it? Yeah? Are you getting it? Your ethylene diamine gets attached like this. So this is also optically active. This is also optically active. Why you know? Because this is in the top front, this is in the back like this. Okay, that's why remember this is also optically active. This is also optically active. Is it clear? Is it clear? Sarjan, Jason, and is it clear? Okay, you what you have to check, you have to do your imagination and you have to check for the plane of symmetry. Okay, you have to check for plane of symmetry. If plane of symmetry is present, then it is optically inactive. If plane of symmetry is not present, it is optically active. Simple. Simple as that. Simple as that. Clear? Come on, write it down and done. Draw it and done in the chat box. Come on. Draw it and done in the chat box. Draw it and done in the chat box. Draw it and done in the chat box. Done? Okay. Okay. Done. Fine. Now, what we have? So, the next topic that we have is the VBT. Okay. I'll just give you the overview and I'll leave it. Okay. In the next lecture, we will start the VBT. I will just give you the overview now. Okay. I'll give you the overview and I'll leave. Okay. Don't worry. VBT. Yes. What is the full form of VBT? Anyone? What is the full form of VBT? Yes. Very good. Everyone is awake. That's why I asked you. I know all of you know this. Okay. I was just checking that you have gone to sleep or no. Valence bond theory. Okay. We have done in the booster batch also VSEPR. Yes, in the booster batch we have done VSEPR. Correct. So similarly, we have something called as valence bond theory. Okay. Now valence bond theory, as always, we do it with the metals with the variable valencies. Okay. So I'll just give one example of valence bond theory and then we'll wrap it up. Okay. So for example, I have compound like let us say FeCN6. FeCN6. Okay. FeCN6 3 minus. FeCN6 3 minus. Okay. So VBT will tell us about the hybridization. How? Look over here. Fe. What is the oxidation state over here? Calculate. Jason and Sarjan, Prashanti, Rakul, Gopinath, calculate the oxidation state of Fe over here. Yes. Calculate the oxidation state of Fe. Three. Okay, so it is x minus 6, correct, and minus 3, x is equal to plus 3. Okay, so I have Fe plus 3. What is the oxidation? What is the atomic number of Fe? Yes, what is the atomic number of Fe? Yes. Jason, Sarjan, and what is the atomic number of Fe? It is atomic number of Fe. Sarjan forgot. It is 26. It is 26. Okay. So if I write down the electronic configuration, it is 4s2. The valence electronic configuration 3d6. But since Fe plus 3, Jason, I will remove 3 electrons. So it is 4s0 3d5. 4s0 3d5. Now in the VBT, the rule is, Sarjan, Jason, the rule is, if you have a strong ligand, electrons will pair. Okay, Cn is a strong ligand. I will give you the list of strong and weak ligand. Cn is strong ligand. Okay, so it will force all the electrons to pair. Okay, for example, what will happen over here? In this, I have 3D. I have to go in this order: 3D, 4S, 4P, 4D. No matter what, I have to go in this order. Okay. I have to go in this order: 4P, 4D. Okay, over here 1, 2, 3, 4, 5. Okay, so now what I have? 5 electrons, so that will pair. So I have a 5 electron, that is the ground state of Fe plus 3. Okay, this is little bit of exception. I will tell you. This is the ground state. In the excited state, what will happen? All of them will pair. So 5. 1, 2, 3, 4, 5. Okay. And one ligand donates how many electrons, Jason and Sarjana? How many electrons one ligand donates? Yes, ligand is what? Ligand is a donor atom. So it donates, it forms a coordination bond, no? So it donates 2 electrons. How many ligand we have? We have CN6. I have 6 ligand. That means I have 12 electrons. So this ligand, one ligand will give you 2 electrons. So you do not have to feel like 1, 2, 3. No. Each ligand is putting 2 electrons at a time. Okay. So 1, 2 ligand, 3 ligand, 4, 5, 6. 4, 5, 6. So over here, what do we have? We have used the hybridization. How we will get hybridization? Sarjan, Jason, and look over here. We'll get hybridization like this. Over here, you have put the electron. So I have started with D. I have used 2D orbitals. So D2, 1 S orbital, S, and 3 P orbitals. So d²sp³ is the hybridization. Are you getting it, everyone? Jason, Sarjana? Yes, that is your octahedral. That is your inner sphere octahedral. Inner sphere octahedral. Okay. Now that was the drawback of VSEPR. We could not start it with D. Each and every hybridization in VSEPR started with S. Okay. In VSEPR we have sp³d². But with the help of VBT, we can also have d²sp³. That is the major drawback of VSEPR, which was corrected by your VBT. Is it clear? Jason, Sarjana, and is it clear? Come on, write it down and then we'll stop. Come on, write this down. Write this down, the VBT. Yes, Jason.
Sir, there is a lone pair in the d3 orbital, sir.
What happened?
There's a lone pair in the 3D, sir.
So that will remain as it is. That will remain as it is. That is what I'm saying. You do not have to fill electrons like this. Okay, you do not have to fill electron like this. Okay, like 1, 2, 3, 4, then 5, 6, 7, 8. Your ligands put 2 electrons at a time. It cannot put half electron over here, half electron over there. Getting it, Jason? Yeah, it will put 2 electrons at a time. That's why it requires an empty orbital, not even half filled orbital. Getting it, Jason?
Okay, sir.
Yeah?
Okay, sir.
Come on, write it down and done in the chat box. Come on, done. Sarjana, Jason. Jason is done. Come on, Sarjana, finish it. Why is it called inner octahedral? See, inner means what? You are starting with d orbital. Okay. We are starting with d orbital. That's why we call it as inner sphere octahedral. Okay. We are starting with d. If we started with s, no, that means hybrid orbital are starting from outside. The d orbitals what we had. That is where we call it as outer octahedral. Your sp³d². Okay. Both of them are octahedral, but difference is one is inner, one is outer. Getting it, Sajna? Okay. So, chalo, thank you for your time.